at Mangrove. Mangrove is a place which is close around 60 kilometers near to Surat. So there has been an accident in the steam pipeline, and there were some casualties. And I was asked to investigate why the accident. So this is the steam pipeline, and after accident, this is the condition that happened to the pipeline. So when we investigated, we found that the reason for the breakdown in the pipeline was formation of slug and higher back pressure, which created a cyclic slug formation and having a frequency which resonated with a system frequency. So what is this slug and how does it get formed? That's my first point of discussion. So when the steam, superheated steam comes out of the boiler and starts flowing through the pipe, because of the heat loss from the pipe wall, the superheated steam, a part of the steam gets condensed and a part remains in gaseous phase in the, so a part becomes liquid and another part goes into the gaseous phase. So in the most uh, common scenario, there will be a liquid and gas separated by an interface which will be sharp. The liquid will be flowing below and the gas will be flowing above. But if the liquid height is beyond a critical height, this critical height is typically of the order of 5.5 to 0.6 times the pipe diameter. And if the gas velocities are significantly larger, the Kelvin-Helmholtz instability starts perturbations on the interface. So you get an interface perturbation. Now, this perturbation has a tendency to grow on its own because of something called a burn-on effect. So what happens is when this interface rises, there is above the interface there is a cross section which reduces compared to the upstream cross section. What happens thereby is the local velocity here, where and as the local velocity increases, the local pressure drops. So the pressure here becomes smaller to pull the liquid level further. So the interface rises. And it so happens that this instability will grow to touch the upper wall. And when it touches the upper wall, because of the shearing from the upper wall, there will be a tendency of separation of the gas into two gas bubbles with this liquid slug taking up the position intermediate. And as soon as this liquid slug enters and divides the gas into two sets of bubbles, it acts as a higher resisting media to the upstream gas. Thereby, there is a jerk in pressure that flows upstream. And this pressure surge can lead to breakage if there are T-junctions or bends in the pipeline. It itself has a tendency to break smaller T sections or pipe bends. The other point is when this gas bubble moves forward, you can see here there is a stooping down. So the waviness again starts generating. And this cycle, which I have shown here, repeats. And the frequency of the repeating cycle, if it at any point of time matches with the system frequency, then there happens to be a resonance and it can completely destroy the piping system. So this is what created all my interest to carry out research in this area of two-phase flow, gas liquid type two-phase flow. So the gas liquid two-phase flow is complex because the density difference between the two phases which simultaneously flows through the pipe is huge. Gas is of the order of 1, while liquid is of the order of 1,000. So the density difference is of the order of 1,000, which makes the interface and its deformation highly complex. So depending on what is the inlet mass flow rate of the gas and inlet mass flow rate of the liquid, you can expect different types of two-phase flow patterns. Now, before I talk about those two-phase flow patterns, let me talk about the application of gas liquid two-phase flow. You can find gas liquid two-phase flow in petroleum industries, chemical industries, petrochemical industries, geothermal industries, and nuclear industries. And there are several reported accidents in these industries because of the hammering that gets generated due to the intermittency and the periodicity of the slug that flows through the pipe. In addition, because when the gas and liquid flows intermittently, the pipe wall gets wet and dry periodically. Also, the slug has a very high moment at some point of time, and highly flowing liquid slug shears the wall. So there are long-term effects of wall erosion, wall corrosion, etc. First, let me talk about different flow patterns. As I said that depending on what is the mass individually flowing through the liquid and individually flowing through the gas section of the pipe, you can expect different kinds of two-phase flow patterns. So generically in literature, they will talk of three different regimes: separated flow regimes, which consist of the simplest of the stratified flow regime, where you have a liquid which is flowing below and the gas flowing above, which with a sharp interface between them. So ideally, there cannot be a very, very stable interface. The interface will have some perturbation in reality. And when the perturbations grow, it takes the form of wave. And then you say it is a stratified wave regime of the flow. And it still is a separated flow regime because the gas and liquid are distinctly separated. The third phase is a complete wave where you can see the waves, the amplitude of the waves are clearly visible to the naked eye. So these are separated flow regimes. Mathematical treatment of separated flow regimes are easier. You have several front tracking methods. You have volume of fluid method, which can track the interface. So basically, when you go for mathematical treatment, the literature will treat the entire two-phase regime as a single phase flow with sudden jump in properties across the interface. So you've solved the Navier-Stokes equation in the entire domain with properties being changed from the liquid domain to the gas domain as your computation progresses. But the point is, how do you track the interface? So tracking the interface needs additional equations to be solved. So in an incompressible regime, because even if you have a gas phase here, the velocities are not so high, so that the Mach number at any point exceeds 0.3. So in an incompressible regime, you can always track the interface by certain scalar functions, like let us say volume fraction. So you talk of a volume fraction, which gives you a ratio of the volume of liquid to the volume of gas in any cell in computational domain. So, and you generate an advection equation for the volume fraction, which is based on the mass conservation. Then you numerically solve that advection equation, the volume fraction for the volume fraction, and you get the volume fractions. So in those computational cells where the volume fraction will be between 0 to 1, so you say that volume fraction in liquid phase will be 1, the volume fraction in the gas phase is 0. But wherever in the computational domain in your cells, the interface passes through, the volume fraction will be between 0 to 1. And then you take an iso contour of a zero point 0.5 volume fraction, and that gives you the interface. So at every point of time, numerically, you solve the Navier-Stokes equations, utilizing the velocity field with the property jump being given across the interface. So the liquid properties in the liquid domain, the gas properties in the gas domain. After the velocity field and the pressure field is established, you utilize the velocity field to solve the volume fraction equation, obtain the volume fraction, and use the volume fraction to generate the interface. So separated flow regime, as far as separated flow regime is concerned, there are a lot of numerical treatments available. So we may actually not do experiment, but capture it numerically. However, the complex regimes, even annular flow regime, which is a separated regime. So annular flow regime is one which happens at a very high gas flow rate. So the gas flows at such a high velocity that it creates an annulus with the liquid surrounding the wall of the pipe. So near the wall of the pipe, you have liquid phase, and intermittently you have gas flowing. But even if you see here, there is a distinct separation between the liquid and gas phase, and there is a clearly demarcated interface which you can capture with all these volume tracking methods like volume of fraction, volume of fluid method. So as far as separated flow regime is concerned, you can always say, why do I look for an experiment which is very costly? I do numerical simulation. But come to the next regime called intermediate flow regime. You see here, you have a gas bubble, and a liquid, which is intermediate between them. Now, when will this gas bubble be separated? What will be the liquid length? All these things depend on the, the, the local conditions of the flow. This is still okay to capture numerically, but look at this regime. This is called a slug flow regime, where you have intermediately bubbles being generated, liquid bubbles or gas bubbles. Here you see gas bubbles in the liquid phase being broken. So how do you talk about capturing so many interfaces where there are bubbles inside? So this is a mixed zone. So this slug flow is impossible to be captured with volume tracking method. You have to follow a Eulerian Lagrangian kind of a technique where these bubbles are to be treated as Lagrangian particles. Even then it is very, very difficult because you do not know the size of the bubbles, shape of the bubbles. So these days there are population balance kind of treatment, but population balance in a domain which you don't know when will it appear. So there is no other way but to do experiment to analyze and understand all the characteristics of this intermittent flow regime. Then you have a dispersed flow regime, which is a bubbly flow regime. Here again, there is only one way to capture it by an Eulerian Lagrangian formulation. When the dispersed bubbles are larger in number, then the approach followed is an homogeneous equation being solved with fluid properties being varied, accounted for by the bubbles being assumed to be spherical and uniformly distributed. That's the approach numerical experts will follow to capture this first kind of a flow regime. However, this intermittent flow regime, there's no other go but to do experiments. So I will show you some of the videos which are being captured in our experimental test facility. This is a stratified regime. You can see the interface between the two phases very clearly. This is a wavy flow regime. You can see the wave, the interface, which is in the form of a wave separating the two phases, and the wave is moving. Then you can have a wave which is called a roll wave, and this is actually, our observation says, is a precursor to the slug formation. So if you see here, this wave curls, this wave breaks here. Now, how do you capture this numerically? You do not know when it is going to break, and you see what is happening after breakage. There are dispersed bubbles which are getting spread. So roll waves is the starting point from where your numerics will fail and you have to go for experimentation. Then you have plug, which is having a gas bubble, another gas bubble separated by a liquid domain, which is actually attached to the wall here. This itself is the starting point of your intermittent regime. And then the slug. You see how the slug flow happens. So this is the interface which is growing, then breaking, attaching, and allowing a liquid slug to separate the two gas bubbles. So a single gas bubble, the gas stream that was flowing, is being bifurcated into two gas bubbles, and then you see the regime of the liquid slug increases, thereby opposing or resisting the motion of the upstream bubbles, while the downstream bubble moves in a very faster speed. So a slug flow has a liquid slug. This is the liquid slug. Bubbles, elongated bubbles, and a film. The film, liquid film, is below the bubble. So there is a liquid film, a liquid slug, a set of elongated bubbles, and how they are distributed will all depend on the inlet flow configurations. In fact, when we started our experiments, we also took care of the steam boiler and the boiling flow flowing through the pipe. But then later on, we realized it's too difficult to control the temperature aspect. So then we resorted to isothermal experiments, which actually generates all the characteristics that we wanted to capture. So we resorted to talking about only isothermal regime later on. So slug flow you can find in gas, oil and gas wells, crudes through transportation of crudes through pipeline, cooling of nuclear reactor, then steam, condensation process in power generation, in handling of transport for cryogenic fluid. And what happens typically when slugs are formed? There is an intermittency in the flow structure. So there's a large variation of gas and liquid flow rate locally, because of which there is a surge in pressure and there is a large pressure drop. And this high momentum liquid slug can change the direction depending on what is in the downstream of the flow. If there is a bend, if there is a T-junction, then it causes more trouble. And then as far as heat transfer is concerned, this is good because it increases the convective heat and mass transfer. So if you look at a micro channel heat sink, where we are today looking for electronic devices, heat capacity, heat release rate of the order of 1000 watt per centimeter square. If you can create slug, you will have a very high convective heat transfer coefficient. In fact, one of my student and his group is working on micro channel heat sink, and we could see 350 watt per centimeter square of heat release when we generated slug flow through the microchannel. So when you talk of heat transfer, slugs are beneficial, but otherwise through chemical flow, they are really going to erode and corrode the pipe in the long run. Possibility of low frequency slug resonating with the pipe structure and breaking it at some point of time. So that's the kind of background which created my motivation to take up research in the area of two-phase flow, gas liquid type two-phase flow. These are the catastrophic failures which we had captured, which are available in literature. In Canada, there is Wal Ahmed and his group who are actually from chemical background. They are looking into this erosion corrosion. At some point of time, we utilized some of that data to develop a erosion corrosion regime map and supplied it to GIPCL So which regime they should operate so that they can avoid erosion and corrosion in the long run. You can see the erosion inside the pitting of the pipe wall because of long-term flow of slug to it. The cracks that develop on the pipe over a longer period. Sometimes because of the frequency, because of the frequency of slug, there are vibrations in the pipe. These vibrations tend to bend and break the pipe as well. So all these failures are possible because of slug flow through pipe. So typically now, I hope I have, can I talk to some of the participants now before I go forward? Can I get introduced to some of the participants? Yeah, I see Azim Safi Loan. Can I talk to Azim Safi Loan? Hello?
Hello.
Hello, am I audible?
You are audible, but your screen is not coming. Now you just share your screen.
Yeah, I have taken away.
हाँ
I
बस
just
बस
wanted
बस
to,
बस हाँ
yeah,
हाँ
I wanted to interact with some of the participants if they are available.
but nobody is asking you anything.
Yeah, no, I just wanted to know whether the background is
No, it's
okay with,
everything is fine.
yeah. Uh, Arif Bilal, is he there?
हाँ
Arif Bilal?
अच्छा आगे बिलाल हाँ आगे बिलाल yeah you want to
Yeah, Arif.
आगे बिलाल you want to ask something.
Yeah,
No, he's not.
okay. Okay, then
Later
I'll
on you
go
can ask.
ahead,
You can
assuming
come
that
up.
what is being talked about are being picked up. Okay,
हेलो
yeah, Arif Bilal, are you there?
जी सर जी सर
Yeah.
You want to ask something?
Would you like to ask anything of the background
नो
that has
सर
been talked? Did you get a feel of the background?
यस सर बैकग्राउंड में शोर आ रहा है
Hello? Hello?
सर
Hello, sir.
बैकग्राउंड शोर आ रहा है
Hello? Yeah, Arif, you would like to say
जी
something?
Later on, he
बैकग्राउंड
will.
में
I
शोर
think
आ
he
रहा
will
है
ask you this thing. If he is having some confusions, if he is having some
Okay,
doubt.
Is Amit Kumar there? Yeah, Amit.
Hello.
Yeah, Amit, is the background okay with you?
Yes, yes, sir.
Okay, shall I proceed?
Yes, check it.
Hello?
You can go ahead, Professor
Yeah,
Banerjee. You can.
okay, no issue.
No
Okay,
issues. Everything is
major
fine.
issues that was there in our mind while we took up this research was first to identify all kinds of patterns that can happen in gas liquid two-phase flow. And then create a flow regime map. So I wanted to know what flow rates we must operate, what flow rates individually to the gas, individually to the liquid. Because the accident that happened in GIPCL was because the person who was operating the control valve operated it much faster than he was expected to, which allowed a larger mass flow rate of the gas to flow over the liquid, creating a sudden wave to rise and block the passage. So what mass flow rates of individual phases that we must operate on so as to avoid slug is the overall strategy. In that process, the first target was to see at what parameter space, what kind of a flow regime you obtain. So generating the flow regime map in general, then identifying the slug regime in the flow regime map, which is the parameter space where slug will be generated, so that industry will always avoid operating at mass flow rates that can lead to slug. This is not only for short-term accidents, but also for long-term erosion of the pipe. Then we went to slightly on the research front to find out the aeration mechanism in the slug. So typically it is the air inside the liquid slug, which is the cause of all kinds of erosion corrosion, because these bubbles collapses on the wall, causes cavitation type of fitting on the wall. So what is the mechanism of aeration? We wanted to fundamentally know through experiments. Because numerics, I said, is nowhere going to capture this exactly. And then we wanted to know, we wanted to tell the industry how they can avoid slug formation. One, what regime to operate, how to sense whether there is a possibility of slug formation now onwards has been the other target for us. So for this, I went to Department of Science and Technology, ACRB, with a project proposal. With this background, I told, if you fund me, I'll be able to do lab level experiment at my laboratory, and I'll be able to tell the industry the flow regime they should operate. I will be able to tell them what kind of troubles they can face, what kind of erosion, corrosion that can happen. Initially, I started with heat transfer also. In fact, I installed a small boiler. I started with steams being blown. But then that was started with a seed grant taken from my institute. But later on, handling heat transfer, that too, temperatures above 100 degrees centigrade in the boiler and in the downstream pipe was slightly difficult in lab scale. So I asked for all the funding for an isothermal test facility. So this is the test facility which I have established in my laboratory. It has a 15-meter long test section. There are 3 pipes that we work on: half inch, 1 inch, and 2-inch diameter pipes. So typically 50 millimeter, 25 millimeter, and 12.5 millimeter diameter pipe. We use 3 different pipes because we wanted to give a non-dimensional set of parameter space. Because in industry, the pipe diameters are significantly larger, and if I have to come to industry level of pipe diameter at the laboratory, then the length that I will require will be typically of the order of 300 to 500 meter. In the lab, I can have spaces of the order of 15-14 meters. Accordingly, experiments could be conducted in diameters of the order of 50 millimeter pipe. Because I need to create stable slug, I need to create stable stratified flow for observation, for visualization, and then going ahead to characterize it. So this is the test facility that I have created. Typically, I need to supply air, I need to supply water. So there is a air circuit, there is a water circuit, and I have this test facility. I have the provision to incline this entire test facility, because in petroleum industry, in petroleum pipelines, which goes from crude to the industry, which are laid on ground, there are always possibilities of inclination, because there will be valleys over which the petroleum pipelines are to be laid. So I need to also know what is the effect of inclination on the flow regime map. So Mahesh Vaze, my first PhD student, had looked into the effect of inclination, which I am not going to discuss here. And we have operated till 10 degrees plus and minus, 5 degrees negative and 10 degrees plus, to see what is the effect of inclination on the flow regime map parametric space. Now, typically, the test facility has a air circuit. There is a screw compressor. We use a screw compressor because it doesn't induce any kind of a vibration into the main test section. And the screw compressor pipe is a long enough pipe so that even if there are smaller vibrations, it doesn't get transmitted to our test section. Then you have a water circuit. We are doing this experiment purely for an isothermal scenario. So there is a heat exchanger with a thermocouple which maintains and measures the temperature. The flow is recirculated back, and before it is circulated back, we have a heat exchanger which brings down all the heat that has got generated during the flow and brings down to the isothermal condition we want to operate the setup at. And then all the visualization I do with a photon fast cam camera, and it's a very high speed camera. So we are able to take up 36,000 frames per second, but we operate at a lower frames per second to get the 3D quality HD vision. So up to 10,000 frames per second we work on. And then you have we also do experiments with pressure transmitters, and that's our take on industry, that because industry puts up pressure transmitters on their pipeline, how the data sensed from the pressure transducers can be used by the industry to avoid, to know when the slug can get generated and to avoid formation of slug in the pipe. So the airflow circuit has this screw compressor, a filter, and a Coriolis mass flow meter, and a pneumatic valve. This is just to control, because we are all on SCADA. Our system is completely on SCADA, and we are able to give a feedback and then check whether the mass flow that we have given on the computer screen is exactly being manifested on the pipeline. Even the water flow circuit has a pneumatic valve, a Coriolis mass flow meter with a heat exchanger, and then the water tank along with a PT100 sensor which checks the temperature at the inlet. The SCADA system that we have, it exactly maintains the mass flow rate of the individual phases that we desire to flow through the pipe. The biggest difficulty we had while we started our experiment was to design the mixer, where the water and air will mix. And we wanted at the end of the mixer, within a very short regime, which we say as the entry regime, all the perturbations must get diminished. So it's the perturbation free field that enters, because I said even smaller perturbations grows by Kelvin-Helmholtz instability here. So we have a pipeline for the gas where there are number of holes at different distances, and the diameter of the holes, if you look at, the diameter decreases from 4 to 3.2 to 1.5 diameter hole. And then there are 8 positions here, then there are 5 positions here where holes are drawn, and there are 3 positions on where holes are drawn, so that we have equal distribution of mass of air being thrown into the liquid while the liquid enters here. So this was a big exercise to set up a mixer which will really make the flow enter into the test section completely perturbation free. This has taken a lot of time, around 4 to 5 months, to finalize the mixer design. Our test facility has pressure sensors. So there are typically 5 pressure sensors for all the pipes. You can see these are piezoelectric type of pressure sensors, very, very precise. The ranges of pressure that they can measure are also given here. So one of the tapping for the pressure sensor is at 3-meter distance from the entry and at 11 meters. So we are able to take a overall pressure drop up to 8-meter length. So, and we get the delta P per unit meter per what is the del P by del X, pressure drop per unit length, by these 2 pressure sensors which are kept at the inlet at 3 meters from the inlet and at 11 meters from the inlet. And for pulsation of pressure, because due to slug or a wavy regime or due to plug, we have installed 4 other pressure transmitters which are very close by. One at 8.175, 8.725, 9.275, and 9.825. These 4 transmitters were used to see the surge in pressure, the stability of the slug. All these things have been analyzed using these inner pressure sensors. In addition, I told you I have got an LDV system in my lab which allows me to go deeper into knowing the velocity field in the liquid, because in the LDV system we put glass particles stressors or silver particle stressors Generally, I use glass particle tracer. Silver particle is only for final measurement because the illumination becomes significantly larger. And these tracer particles only mixes in the liquid phase. So I am able to track the local velocities in the liquid phase using my LDV. We have three component LDV, but whatever we could very successfully do as of now is one component of the velocity, the major X component we could track. The second component and third component, because of the intensity, it's not so, we are not confident of presenting it to the research journal papers. So I'm not discussing that at present. There is one big issue because of the curvature of the pipeline. So because of the curvature, the distance at which the focal point of the two beams should be slightly get distorted. So what we did is we created a rectangular section with the same liquid properties, so that we overcome the curvature effect due to the pipe. And then we have also, when we got the laser, there was a small amount of fringe shift that we adjusted with the calibrator that we had. Our measuring section has a mixing zone in the beginning. So typically 2 meters of section for each. Then there is a developing zone. There is a visualization zone. There is a pressure measurement zone. And at the end, I have the velocity measurement zone. So this is where I have created this rectangular section where for all the pipes, and I have a traverse mechanism. I forgot to tell. This is a 3D traverse mechanism which allows this transceiver probe to move in all the three directions by 0.1 millimeter of precision. So I am able to travel from the pipe wall to the center of the pipe on both the directions up to 0.1 millimeter. So I am able to get the complete three-dimensional image of the velocity field in the liquid phase, obviously not for the gas phase. And because the measurements are only possible in the liquid phase, we have developed a novel strategy to get the liquid height also utilizing the LDB probe, which I shall discuss later on. So these are my measuring sections. Now, when I talk of fundamentals and I go into my experiments, I need to clarify two parameters. So because there are two phases here, not a single phase, we do not have any idea about the local velocity, because if I look at this pipe section, a part of the section is occupied by the gas, part of the section is occupied by the liquid. So what is the cross-sectional area of the liquid is not known. What is the cross-sectional area of the gas is not known. What I know is only the cross-sectional area of the pipe, that is the diameter of the pipe. How much fraction of the diameter is occupied by the gas, how much fraction of the diameter is occupied by the liquid is completely dependent on the inlet mass flow rate. So I cannot talk about phasic velocity here. Liquid phase velocity, local liquid gas phase velocity, no possibility. So what we talk of something called a superficial velocity. Why do I talk of superficial velocity? How do I talk of superficial velocity? And also associated Reynolds number as superficial Reynolds number. Now this is important to be noted. What is the superficial velocity? Superficial velocity is the velocity that the fluid will occupy if the same mass of one of the phase is allowed to flow through the entire pipe. So supposedly I allow the entire liquid phase, this mass flow rate to flow through the pipe, or the gas phase, this mass flow rate to flow through the entire pipe. Whatever velocity I expect is the superficial velocity of the phase. So because the cross section occupied the phases individually is something which cannot be known a priori, we have to talk through superficial velocity and correspondingly the superficial Reynolds number. So typically the superficial velocity is decided by the mass of the phase. So if K is the phase, K is liquid, then mass of liquid which is supplied from the inlet which I measure through my Coriolis meter, gives me the superficial velocity, assuming the complete cross section of the pipe, where A corresponds to the complete diameter of the pipe, and then correspondingly the Reynolds number, superficial Reynolds number, where again the characteristic dimension that I use is the diameter of the entire pipe, because the diameter or the cross section occupied by the individual pipe is not known. So typically we play with these two parameters, the superficial liquid velocity, superficial gas velocity, which is a dimensional parameter, and in non-dimensional form, the superficial liquid Reynolds number and superficial gas Reynolds number. So when I talk about uncertainty of my experiment, typically the derived variables are the superficial velocity of the liquid phase, superficial velocity of the gas phase, superficial liquid Reynolds number, and superficial gas Reynolds number. And all of them will depend on the mass flow rate. So my uncertainty of the derived variables, which are the liquid velocity, superficial liquid velocity and superficial gas velocity, or the superficial liquid Reynolds number or superficial gas Reynolds number, depend on the accuracy of the measurement of the diameter, accuracy of the measurement of the mass flow rate, provided the properties are known correctly. So we did an uncertainty analysis based on the United Kingdom accreditation services to obtain, based on the errors associated with the pipe diameter. So our 12 pipe diameter, it varies from 12 plus or minus of 0.833 or 20, because the entire cross section of 12 millimeter is not possible. This is the error. Our 25 millimeter pipe is 25 plus or minus 0.6. 50 millimeter pipe is 50 plus or minus 0.4. The mass flow rate of air, the error is of the order of 0.38%. The mass flow rate of water is of the order of 0.13%. These are the errors in the measurement. Based on these errors, the uncertainty generated for the superficial Reynolds number of liquid, superficial Reynolds number of the gas, all of them are being noted here. 0.916% for 12 diameter, 0.710 for 25 diameter, 0.552 for 50 diameter. These are the uncertainty in the derived variable in our experiment. Everything, if you see here, the maximum uncertainty in the superficial Reynolds number for a very small diameter pipe is 2.529, and for superficial glass Reynolds number is 2.748%. Everything is less than 3%. So very, very precise measurements, with precise estimation of the derived variable is possible in the experimental test specimen. Okay, now with this introduction to the experiments the facility that we have, I would like to go to my results and discussion, which will be in parts. Part one is the flow visualization. Any questions from anyone? I'm open to it. Yeah.
So, Professor Banerjee, I have a question.
Yeah,
So you were
please.
talking about the slug flow.
Yes.
So bubbles are being formed. So can you tell us some idea what is the frequency of this bubble formation? So
Yeah, that depends on the inlet mass flow rate.
okay, fine, fine, fine. But
Yeah, it's
sometimes
not known a priori. Yeah.
okay, 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 okay. And you were talking about that you had scaled down your this thing as a facility in your laboratory. So what was the scaling ratio? Scaled down up to what extent you have? What was the
No,
scaling down
no,
ratio?
no, no. It's not typically scaling down. It is all about lab scale experiments that I can do. Then it
Okay,
has
yeah,
to be
yeah.
scaled up for the industry.
Okay, okay.
Yeah. So in the lab, supposedly I want to do precise experiments. I need to have length to diameter ratio, typically value of length to diameter ratio, which is more than 200.
Okay, 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 that's
So
fine.
if I think of the industry level pipes, which are, let us say, 500 millimeter diameter, you can imagine what length of the test section I should have.
Oh, yeah, yeah. It would be very this thing.
Yeah. So typically in the lab, we can do experiments with these smaller pipe diameters, and everything, because we are doing experiments on 3 diameters, we
Yeah.
are putting down into non-dimensional form. All are discussed through Reynolds number, superficial Reynolds number of liquid and gas.
Okay,
So
that's
it's
fine.
non-dimensional. Then depending on the pipe diameter in the industry, you can scale the values to this dimensional scale.
One of the
Okay.
participants has raised his hand.
Yes,
Mama
please.
Dilabag, you want to ask something?
Yes, somebody.
Dilabag.
Hello, sir. Good evening, sir.
Good
This is
evening.
Mohammad
Yeah,
Dilawar, sir.
Dilaver, please tell me.
Yes, sir. I am working in heat transfer lab at NIT Srinagar, sir. Sir,
Yeah,
I want to ask few questions, sir.
yes, please.
Uh, Sir, pipe thickness also important parameter.
True, true,
Uh, and
true.
sir, other question is, sir. Uh, Sir, I am working on nano refrigerant, sir.
You are
In
working on
refrigeration system, nano
refrigerant.
refrigeration,
Yes.
nano refrigeration,
Yeah, yeah.
refrigeration system. For example, in condenser coil, sir. So we are using the coil diameter is 5 mm coil
Yeah.
diameter, sir.
Mm-hmm.
If I decrease the coil diameter, sir, from
Mm-hmm.
5 mm to 4 mm,
Mm-hmm.
so at that time I need less charge of
Mm-hmm.
refrigerant, sir. Okay,
Mm-hmm.
so we can save the charge.
Mm-hmm.
Sir, at that time the pressure increases, sir,
Yeah.
inside the pipe pressure increases. So shall we need to increase the thickness of the pipe?
For what?
For example, if I decrease the diameter of the pipe, sir, so
Yeah.
what about the thickness of the pipe? Shall we go for the same thickness?
Okay. Now, as far as these experiments are concerned, the diameter that I am talking about is the inner diameter. Okay.
Yes, sir.
Inner diameter through which the fluid flows.
Yes, sir.
Okay.
Yes, sir.
So the thickness is not coming into my discussion, because the diameter through which the fluid is flowing is the inner diameter.
Okay, sir.
Is that clear?
Okay, sir.
My discussion is all for inner diameter of the pipe. Now, for your case, I don't know. If you reduce the diameter in the scale that you are talking about, the the forcing function that will get more importance is the surface tension force,
Yes, sir.
which in my case is almost absent because I am talking in macro scale.
Yes, sir. Yes, sir.
So surface tension will obviously depend on the surface quality, not not the thickness,
Okay, sir.
quality of the surface. Correct?
Okay, sir. Thank you, sir.
Yeah.
Anyone else? One more participant has raised his hand. You can also ask the question.
Hello,
Hello?
good evening, sir. My name is Danish Ashra.
Okay.
Yes,
Sir,
please.
sir, my question to you is, as you said that slug increases heat transfer coefficient,
Yes.
but in case of heat exchangers, as there is a term called fouling factor,
Hmm.
which I guess is related to this slug.
Yes.
And if slug increases heat transfer coefficient, then how effectiveness of heat exchanger decreases by when a slug is there, when fouling factor is there, when
No.
fouling occurs in.
Okay. Why slug increases the convective heat transfer coefficient is the slug has a very high momentum. And if you look at the velocity distribution in the slug, if you think of a simple water flowing through a pipe, you've got a parabolic profile. If you look at the velocity distribution in a slug, it is logarithmic. So almost the wall is getting connected to a very high velocity, which is closer to the central line pipe diameter, pipe velocity. That is why the forced convection heat transfer is very, very high for slug.
Okay, thank you so much, sir. Thank you.
Yeah.
Anyone else?
Okay. So now I start with
Sir, you are
the
stating
yeah, yeah. Yes, please.
hello, sir. My name is Alok Ranjan Yadav.
Yeah.
I'd like to ask, sir, that you are studying since you earlier told about the theme of your presentation, that you are working on getting rid of the fracture that occurs in those pipes with this slug formation.
Yeah.
But and since it's very frequent and the reasons behind are mostly related to the fluid, fluid that has carried some of the sediments or some of the particles which are cannot be
Yeah, yeah. But
yeah.
presently the experiments are with pure liquid and pure gas.
So I
Particles
mean,
do contribute significantly to the instability. Yes.
yes, so I mean, so you are taking these conditions more like keeping all of these things idle. Also, you are,
Yes.
I mean, stating a hypothesis or just it's a empirical formula. I mean, empirical study taking it into account everything.
Okay.
Because someone was also mentioning about surface tension, and I was like very much, curious how surface tension is a predominant factor while in the study of these things,
Not
and
this. In this experiments, the surface tension is not predominant. If your dimensions become smaller and smaller, the surface tension force will become dominant. So in the question that was asked, which was for refrigerating pipes, where the dimensions are in mini dimensions, mini scale, not macro scale, their surface tension is predominant. Okay,
and sir,
now to answer your question about particles, no, in a liquid. Now, in different industrial scenarios, there will be different kinds of particulate matter that will flow. Correct? Am I correct?
yes, sir.
And different. So, in a lab scale, how do you incorporate those? Yes, we can always extend our experiment by adding known amount of particulate matter. Correct?
Yes, sir.
Yeah. So experiments are done with a very ideal condition where we have very pure liquid. In fact, the water that we supply is filtered through an aqua guard and then put into the water tank. So ideally, so my answer to your question is the stable regime that I am talking about here will shrink in case of the liquid being contaminated or gas being contaminated. So hypothetically, I know a larger safety regime, and when I have to work with a adulterated liquid or adulterated gas, my regime will be smaller, so I can work with a safety factor. Correct?
Yes, sir.
I hope that answers your question.
Yes, sir. Yes, and that also explains why those you were talking about that overall heat transfer coefficient and its
Yeah,
effect on
yeah,
the post convection. So yeah.
yeah. Okay, Adnan,
It's fine.
can I go ahead?
Yes, sir. Go ahead, please.
Yeah. So I typically have 1 more hour, correct? Hello, Adnan?
Please go ahead. Please go ahead.
I have 1 more hour, huh?
One more hour. 50
Okay.
minutes you have still.
Yeah, what do you say?
50 minutes.
50 minutes.
Uh,
Okay.
okay.
So the first part was the visualization of different flow regimes and developing the flow pattern map. So what are the different flow regimes that we can expect? This is only for horizontal pipe. We can expect a stratified flow. We can expect a wavy stratified flow. We can expect a wavy flow. We can expect an annular flow. We can expect completely bubbly flow. This is a separated flow. And we can expect the dispersed flow. We can expect intermittent regime of slug and plug. But when do you expect different, what parameter regime you will see what kind of a flow is the question. So what we do, so we develop something called a flow pattern map. So flow pattern map has two axes. One of the axes will talk about either the liquid superficial velocity or liquid superficial Reynolds number in a non-dimensional form. The other axis will talk about the gas superficial velocity or gas Reynolds number. Sometimes people talk with in terms of Froude number also in a gravity driven domain. Our experiments are all for closed domain of pipe. So not open channel kind of experiment. So it is only Reynolds number which is predominant, and it's all horizontal. So what we do to find out the parameter space for which the different regimes will appear, we utilize flow visualization. So this is the flow visualization section that we have, and we use a camera to capture the images that flows, and there is a high illuminated studio light and a white board behind to give you the quantified parameters as well. So what we do for getting the flow pattern map is this axis is your superficial gas velocity. In non-dimensional form, it will be superficial gas Reynolds number. This axis is superficial liquid velocity. Non-dimensional form, it will become Reynolds number, liquid Reynolds number, superficial liquid Reynolds number. And we start with one gas velocity and one liquid velocity. So this is my point. So this corresponds to one set of mass flow rate of gas, one mass flow rate of liquid. So for this is the corresponding point. Now we do experiment at with an inlet mass flow rate of liquid corresponding to this value, with an inlet mass flow rate of gas which corresponds to this value. And with our visualization tool, we visualize what is the flow regime that we capture. So if this is the kind of flow regime which is captured, we say this set of mass flow rate of liquid and inlet mass flow rate of liquid and gas corresponds to stratified flow. Now, after we have established this, we increase the mass flow rate of liquid further. We reach to another point. Again, we conduct the experiment. We visualize what is the regime flowing for this combination of liquid mass flow rate and this combination of gas mass flow rate. So if we see waviness on the interface, we say it is stratified, wavy stratified flow. We move further. We go to another value of liquid superficial Reynolds number or liquid superficial velocity only by increasing the mass flow rate of liquid. The gas mass flow rate is fixed. We are increasing the liquid mass flow rate. And then through our SCADA, we are establishing that we have maintained the correct mass flow rate of liquid and gas, and then start our experiment of visualization, continuous flow visualization. And then if we observe this kind of a regime where there are two gas bubbles separated by liquid slug, which is again filled with bubbles, then we say this is a slug flow. This combination of gas and liquid mass flow rate corresponds to slug flow. Similarly, we go further. This combination corresponds to plug flow. This exercise is done for another set of mass flow rate of gas. Same for other set of gas. Same for other set of gas, and we continue. Then in this parameter space, we will be able to know what combination of mass flow rate of liquid and gas, or what combination of liquid superficial velocity and gas superficial velocity, or what combination of liquid superficial Reynolds number and gas superficial Reynolds number will give what kind of a flow regime. This is a flow pattern map that we develop. So these are the images. So I have a superficial Reynolds number of 708 and gas Reynolds number of 823. This is the image. I got a stratified flow. I kept my liquid gas superficial Reynolds number constant, increased my liquid superficial Reynolds number from 708 to 4951. I got a slug flow. Increased it further, 9880. I got a plug flow. Then I kept my liquid superficial number constant and went on varying my gas superficial number. I will get different sets of flow regimes. Some of them will be individualistic, like a clear-cut stratified flow or a clear-cut slug flow, or a plug flow or a wavy flow. Some will give a mixed, sometimes it is slug, sometimes it is wavy, sometimes it is slug, sometimes it is bubbly. So these are mixed flow regimes. Sometimes it is wavy, sometimes it is annular. These are mixed flow regimes. Sometimes it is slug, sometimes bubbly, sometimes annular as well. Mixed flow regimes. Then what we do is, so let us say we have taken all these combinations, 36 stratified, clearly stratified, 12 clearly wavy, some of them 16 which are slug wavy, 24 points which are wavy annular. All these points now we plot here. And the boundaries are separated by the transition line. Now I know that this is the regime A, where you always get stratified flow. That means if you operate with mass flow rates which varies from 0 to 10,000 of superficial gas Reynolds number and mass flow rate of liquid which varies from 0 to 2,000 of 2,200 or 2,500 of liquid superficial Reynolds number, you always expect a stratified flow. Then if you operate in this regime, which is bounded, separated by this boundary, you expect a wavy stratified flow. If you operate in this space, parametric space, you expect an annular flow. See, you get an annular flow, which is at a very high gas velocity because the gas velocity is so high that it is able to pierce through the liquid, putting the entire liquid into the near the wall. Is such a high velocity of the gas. If you are operating in this parameter space, you expect a plug flow. You have bubbles which are separated by a liquid plug. If you operate in this regime, you get this kind of slug flow, where there are bubbles which are long gas bubbles separated by a liquid slug, but the slug itself has small bubbles, and you do not know what size, how they will agglomerate, how they will collapse on the wall. Then if you operate in this regime, you get a bubbly flow. This can be treated with a homogeneous mathematical model. So this is how you generate a complete flow regime map. This is a flow regime map we have developed in 2013 and published in International Journal of Multiphase Flow, if I recall it correctly, or maybe flow visualization. Now, this gives you all kinds of flow regimes. So this map, if I give it to the industry, now they know, well, if I want always a very stable stratified flow, I never operate beyond this regime. So industry knows I should never operate beyond this regime of mass flow rate if I want to always get a stable stratified flow. So even if I increase my gas velocity, I can operate in this regime. Still it is stable because I'm going to get either wavy or a stratified flow. But if I work in this regime, I'm expecting slug. So I should not increase my liquid mass flow rate larger than this so that I create trouble for my industry. That's how it is useful to the industry. Now, my target was not only to talk about all the regimes, was to focus on the intermittent regime, which is the most dangerous, and look at its surrounding so that we can tell. If you get the sense here, don't go beyond so that you fall into the slug regime. So the next part of my discussion is how did we go ahead to develop the intermittent flow subregime, which consists of slug and plug. So now this is my generic flow regime map that I have developed. My focus will be in this zone now, this combination of mass flow rate, where I get plug, slug, and maybe a combination of slug, plug, annular. So I focused in this regime then. My team worked on this regime then and observed three kinds of intermittent flow. One is a plug flow. You can see the plug flow. There is a gas bubble and there is a liquid plug. So this is the gas bubble has a very long tail. This tail is moving, and then you have a liquid slug. But there is no small bubble. These are pure long gas bubbles followed by a liquid slug. So this is a plug flow. It is less dangerous, though it is intermittent, but it is less dangerous for the pipe. But it is an intermittent. See, still you have got a small bubble, but it will merge with the uh, main gas bubble which is coming up. The next gas bubble which is flowing. This is a plug flow. So if I know the regime of plug flow, I can still be assured, okay, I may not have a lot of damage to my pipe. Then the next regime is a less aerated slug. Now you see, this is your gas bubble. This is the liquid plug, but the liquid plug is full of small bubbles. See, these small bubbles, they will collide, collapse, they will agglomerate, they will merge onto the wall at times, but still it is less harmful for the pipe because the bubbles are smaller in number. But this is the next bubble which is coming. Even if you look at the nose of the bubble, there are a lot gas bubble, there are a lot of droplets. Now this is the most dangerous zone. This is called highly aerated slug flow. There is gas bubble, there are liquid plugs, there's liquid plug, and there are small bubbles, larger in number, highly catastrophic, causes erosion and corrosion to the pipe. Now we are going to focus. So for getting the intermittent flow sub-regime, we focused in this range of Reynolds number from 1415 to 18391 for superficial Reynolds number of liquid, 393 to 7461, which we obtained from our earlier study. So we are operating in this regime and we wanted to see what to expect. So now if you see in this regime, if we operate, we can get a slug initiation. So the slug may just touch the wall. It will not create a jerk in pressure. If you are operating in this lower regime, which is very safe, the stratified flow. But above this liquid velocity, in this regime, it depends on a combination of liquid and gas velocity. So basically, there is a critical liquid height beyond which you can have the slug initiating, because beyond that critical height, the Bernoulli's effect will become predominant, thereby pulling up the plug so as to make it attach to the upper wall. And then we found out that if you are operating in this regime, you can get a liquid plug. However, slightly small change in gas Reynolds number can lead to small bubbles, less aerated slug flow. Then you have very highly aerated slug flow in this regime. So obviously the industry will be told never to operate in this range of mass flow rate, but industry has to supply. Many a times they need to do it. So, but we can only tell them, please operate your parameters not to have the slug formation, highly aerated slug formation. Even you can have slug and wavy kind of a combined flow regime in the boundary of my intermittent regime in this zone. So this is a intermittent flow regime clearly showing the plug, the less aerated slug, and highly aerated slug formation zone in our parameter space. The slug initiation needed to be verified. If I wanted to tell the world that I have done my experiments very precisely, I must show validation. And the validation is very essential for the slug formation zone. You can see these are slug formation zone. You see how how these waves grow and then it touches the wall. Even here you can see that. These are slightly low frequency slug. This is high frequency slug formation. So different combinations gives me the transition where from you get either a stratified flow conductor converted to a slug or a plug flow converted to a slug. Now this is being validated with the available experiments. The experiments are done in dimensional space and these are available for 1-inch pipe diameter. So we have validated this with our 1-inch pipe diameter. So you can see that our experimental line is closer to the lines. Again, here the question is why you cannot have a very close map, because the experiments which I am citing here are very old experiments where they could not filter the water as or the air as effectively as we are able to filter it today. But still, there is a close map, and we could publish our results based on this validation of the slug initiation. Capturing slug initiation needs a lot of patience, a lot of time to be devoted for the experiments. So now I summarize this visualization showing the clearly demarcated stratified flow, plug flow, then low aerated slug flow and highly aerated slug flow. So this is my intermittent flow subregime. This we published in 2015 and has been a good hand for the industries. Now, the next target, that the next set of results that I am going to show is we have come to a point, even my discussion with Wal Ahmed in Canada, he has been very, very confident that the main catastrophe that the slug creates in pipe is due to aeration, due to the bubbles, the smaller bubbles. So then I thought, since we have a very good visualization facility, let me do a patient setup experiment to find out what is the mechanism of aeration in slug body. So these are some of the results which are detailed in some of our journal papers. You can see our journal papers in International Journal of Multiphase Flow, Journal of Petroleum Sciences, now Journal of Nuclear Engineering and Design, flow visualization journals, where all these results have been published. So we found that this aeration typically happens either when wavy stratified flow transits into slug flow or the plug flow transits into slug flow. So to capture the transition of wavy stratified flow to slug flow, we took up one liquid Reynolds number, this liquid Reynolds number, and moved forward with number of gas Reynolds number which are near to the transition boundary between the wavy stratified flow and slug flow. If you come here, if you go slightly up, you will get slug. If you get slightly move forward, you will get high aerated slug. So we closely identified these set of Reynolds number combinations and corresponding mass flow rate we supplied. And at each and every point we visualized and we wanted to know how aeration, how air gets entrapped into the liquid slug. And then next set of experiments we did for transition flow from plug to highly aerated slug. For that, we took this higher value of superficial Reynolds number of liquid. I will talk about both. Let me first talk about the transition from stratified flow to slug flow, the less aerated slug and highly aerated slug. I have shown the 4 different sections 1, 2, 3, 4, and this is the video which will demonstrate the 4 different phenomena that leads to aeration in the slug. So if you look at this initially, so again I'll go to the beginning and I'll start from the beginning. If you, okay, I will go back to the beginning of my animation. So if you see, this is this position. I have waviness in the flow, small waviness in the stratified flow. This is complete stratified flow. Now my interface is slightly perturbed. So this is the condition 1 that I am showing. Now I start my video. See what is happening. There is one wave which is slightly higher in wave height, which is following this small wave. This is the second stage, you can see. Now what this wave does, it tries to merge with the smaller wave. See, slowly. So slowly and slowly, this wave, all the liquid is going into this bigger wave. And what it is doing is, first it will increase the width of the wave, and then it will increase the height of the wave. See, this is what is happening. It's a very slow motion video that I am showing. Now you see, these two have merged and it has generated into a single wave. Now, when this single wave starts going upward slowly, see, now it, because of the Bernoulli effect. See, now it touches the pipe. Now this liquid slug enters. Once again, I show. So this is how it is merging. Yeah. So this is the third stage, the slug initiation stage. Now it has grown in weight. Now it is starting to grow in height. Because here the local pressure will drop because of the space available for velocity of gas is low. So mass of gas, this space is smaller, the velocity will become larger, the pressure will become lower, and this will start rising. Once it rises and touches the wall, now it gets separated. See, now this bubble, see, these bubbles are getting fragmented, and they are getting, these liquid droplets, they are getting into the the liquid, the gas bubble. See, so that is how small droplets into the bubble. See this, how the liquid slug gets created, how the two bubbles get separated, and how the liquid droplets get into the gas bubble. Now, this is the second phase. This is the first phase was uh, this separation. Now you see. Now these liquid droplets, how they move forward, how this they are getting entrapped into the bubble. They are getting entrapped. These are getting entrapped. This is flowing with this gas bubble is flowing with lower velocity, and these droplets along with the forward gas bubble is moving with a higher velocity. There are droplets. See, the next stage. The third stage creates multiple rounds of droplets. See, multiple rounds of droplets. That is how it starts increasing the rate of aeration. You see now in this video. See how multiple bubbles are increasing in number. There is a huge swirl created here. This is how high aerated slugs are formed. Once this is formed and it starts moving with a higher velocity, see this video now. Once this is formed and it starts moving with a higher velocity, it will engulf all the wave crusts. See? And see how aerated the slug becomes. See how highly aerated it becomes. This is how the high aerated slugs, this is the mechanism of formation of high aerated slugs. So your wavy stratified flow can lead to highly aerated flow from low aerated slow, low aerated slug flow. Okay, this is one part. The second part, to observe how the aeration happens from plug to slug, we took this value of a Reynolds number of liquid and went in on increasing my gas superficial Reynolds number. Now, if you see, it's the aeration is happening from the bubble tail, not from the bubble nose, or it is happening from the tail. See, from the tail there is separation that is happening, and these separated bubbles will detach. So there are two things that happen. The tail of the bubble goes on getting shrinking. At some point it will get detached. So there is a breaking of the bubble ring. These will break away from one bubble and then get into small droplets, and join to the nose of the next bubble. This is how the plug gets converted to aerated slug. So this is how the mechanism was identified for formation of highly less aerated slug, highly aerated slug, and very highly aerated slug, and at what range of parameter space we could observe them. Then the next section that I shall talk about is slug flow characterization. Now, this characterization, along with understanding of mechanism, has helped us to create a erosion corrosion map, which we have given to GIPCL after the project was completed. So now what we are going to do is we are going to measure slug parameters through our visualization. So how do you measure slug parameters? What are the slug parameters? Slug velocity, the velocity with which the slug moves, the slug length, and the slug frequency. We used our visualization to measure the slug velocity, slug length, and slug frequency. Now, how did we measure? Let us look at the slug. So in our whiteboard, which is behind the pipe, we have all the length scales provided: 110, 115, 120, 120. This is the length scale. In the length scale, we mark 2 points, one blue, another blue, over a distance. This distance is known to us. Now we capture the image. We start our clock at the point where the slug enters this blue line. The slug is entering. And we measure the time when the slug leaves the blue line, the next blue line. So we know the distance, we know the time that the slug took to cover this distance. So by knowing these two, we measure the velocity of the liquid slug. Similarly, the length of the slug, we measured. Supposedly, the slug was larger than this length. Then we could measure it by the time of the lug measured for the liquid slug front and the following liquid slug tail, and multiplying it with the liquid slug velocity. The frequency of slug was measured by counting the number of slugs which passed through the visualization section over a period of time. So these were all done through the videos that we captured. And then we wanted to see what happens as we go on increasing the liquid Reynolds number and the gas Reynolds number. What happens in the plug regime? What happens in the slug regime? What happens in the highly slug regime? So if you look at this here, we are varying the liquid superficial Reynolds number for two values of gas Reynolds number, gas superficial Reynolds number I have shown. What happens to the slug frequency? So if you see, for a low superficial gas Reynolds number, the frequency is high. And the gap between these two goes on increasing as the liquid superficial Reynolds number increases. So as your liquid mass flow rate increases, there is larger frequency of generation of plug. However, gas superficial velocity has little effect on it. The liquid superficial velocity has a higher effect on the frequency of slug. So suddenly, if you increase the liquid mass flow rate, there will be higher number of slugs or less aerated slugs or highly aerated slugs that will be formed. So liquid mass flow rate induces more of frequency. Low liquid mass flow rate can have lower frequency of slug formation. We validated our experimental calculation with the results of Wang and Puza, and we developed our own correlation, and then we checked the root mean square deviation from both the experiments which were shown, and then this was done for a range of parameters for which their experiments were available. but then we could extend our calculations to larger set of parameters because our experiments allowed larger mass flow rate to be incorporated. Similar thing we did for liquid slug velocity. We observed how superficial gas Reynolds number and liquid Reynolds number influences the liquid slug velocity. So if you, for a large increment in liquid slug velocity, a small increment in plug velocity was observed. So all these things we did, we validated for the range for which experiments are available. So these experiments, Benediction's experiments, were done for small range of mass flow rates of liquids and gas, and we validated that first. We developed the correlation and we extended the correlation to obtain this liquid and slug velocity, slug frequency, slug length for all the regimes later on. Same thing we did for slug length. After we did this set of experiment, we knew what is the slug velocity expected in every combination of gas and superficial Reynolds number. Once we have these slug velocities, now we have literature which says that if your slug velocities are beyond a slug frequency is beyond 1.35, or if your plug velocity or slug velocities are beyond 1 meters per second, then you expect this kind of erosion or corrosion. So wherever my slug frequencies and slug velocities exceeded these values, I drew this line. So this line will show beyond this line what kind of erosion, corrosion that I can expect. Similarly, wherever the slug velocities are less than 1.58, what kind of erosion, corrosion are expected? Or is it a slow, safe regime? So in literature, they talked about the range of liquid slug velocity, slug frequency, slug length for different kinds of erosion, corrosion, like fast accelerated corrosion, shear stress induced erosion, cavitation erosion, liquid inertia induced erosion. The regime of velocities, lengths were and frequencies were available. Utilizing that data, we could generate an erosion corrosion map. So we have a parameter space for liquid superficial Reynolds number and liquid superficial gas number, where we can show this is the safe zone as far as erosion corrosion is concerned. So if you operate in this zone, you are in the safe zone. You don't expect any kind of erosion corrosion to the pipe for a longer run. Whatever erosion corrosion that will happen is because of the adulteration of the liquid. For a pure liquid, if you are operating in this zone, you are completely safe. No erosion, no corrosion over a long period of time. But if you are operating in this regime, you expect cavitation erosion. If you are operating in this regime, you expect shear stress induced erosion. If you are operating in this regime, all kinds of erosion corrosion can happen. In this regime, you can have cavitation erosion, fast accelerated corrosion. These fast accelerated corrosions are such that they can even break the protective layers. Some of the industries inside their pipe keep protective layers, which will not allow erosion for longer period. But this fast accelerated corrosions are such that they can even break that protective boundary as well. And the other point I wanted to tell, in industry they are using slug catchers, but the slug catchers are effective for a range of slug. For smaller slugs, it is not able to capture. For larger slugs, it is able to capture. So even the design of slug catcher will significantly be augmented by knowing what slug length you expect in different ranges of Reynolds number. Is that all right? Hello?
Everything is fine.
Okay. I think
But
I'm getting,
you can have a glass of water or take tea.
yeah, yeah.
You're quite exhausted.
Yeah. Okay. So I'll go forward. So this is something which we have given to GIPCL so that they get benefited knowing what regime they should operate. Then with our LDV, we went on to do something very, very precise and very significant as far as research is concerned. We went on to measure the local liquid velocities in the plug, in the liquid film, because only measurement that is possible is in the liquid regime, because the stressor is filtrated in the liquid regime. We don't have any stressor in the gas phase. So no measurement is possible in the gas phase. So, I have already talked about the LDB setup. I'm not discussing it. So first thing that we did is we we validated the measurements with simple parabolic profile, the law of wall that exists in literature, and we have shown that the errors in our measurements are less than 0.5%, the local velocity measurement and its distribution. So the maximum velocity that you expect, the maximum velocity which is measured, and the calculated values based on the experimental, based on the analytical results which are available in literature. Then we went on to see what is the effect of air mass flow rate on the velocity perturbations in the liquid. So what you expect is this is an average velocity distribution. As soon as the liquid regime becomes turbulent, you will have fluctuations, and the scales of these fluctuations are largely varying. Now, turbulence is a multi-scale problem. You can have perturbations. You can see here the perturbations, very small perturbations, very large perturbations. We wanted to see the turbulence level in the liquid phase because of the purging airflow above the liquid. So what we did is we took the range of Reynolds number for which our liquid level will be more than 9.5 millimeter, means 10 millimeter, more than 10 millimeter. And we kept our probe at 9.5 millimeter, 0.5 millimeter below the minimum liquid height possible for all the ranges of Reynolds number for which we did this experiment. So we kept the probe located here, measuring point is here, and then we kept the liquid mass flow rate, which will always keep the liquid level above 10 millimeter, and we started purging air. So this is one set of Reynolds number, which is for 900 of superficial liquid and 750 of superficial gas, where the liquid height was 11.25 millimeter. Now, how did we measure the liquid height? I'm going to tell in my next slide, the liquid height measurement. Now, for this, what is the velocity signal that we, so here when it is completely water, no gas, this is simple water flow. But since the water is itself turbulent, you see small perturbations. These are the turbulent perturbations in single phase water flow through the pipe. So this is the level of turbulence for this liquid Reynolds number of 900. Now I kept the liquid Reynolds number same as 900, but I purged air above and created an air Reynolds number or gas Reynolds number of 750. And what I see, the perturbation you see, the thickness of the perturbation has increased. I still kept my liquid Reynolds number 900 only, and I purged more air mass flow rate, and I increased the gas mass flow rate so as to create a superficial gas Reynolds number of 1500. What happens to the liquid height? See, because air mass flow rate I have increased, this trying to bring down the liquid level. The high purge of air above is trying to diminish. So the liquid level has dropped from 11.25 to 10.75. And see the perturbations. The amplitude of perturbations increases. Further, I increase the air mass flow rate to 2250. See the perturbations that get created. When I increase it to 3000 with the same liquid Reynolds number for which the first experiment was done, you see waviness at the interface. And because of the waviness, you see the perturbation in velocities. See, not only the turbulent scale, but there is a major perturbation in the velocity itself, correct? Which demonstrate the waviness of the interface itself. in addition to the turbulent fluctuations that happens. Now, how did we measure the liquid height? This is a novel strategy that we adopted utilizing the laser Doppler velocimeter itself to obtain the liquid height. So how do we get the liquid height? So the liquid height for a fixed set of Reynolds number of liquid and gas, fixed value of mass flow rate of air and water. So I fix my Reynolds number, I fix my liquid height, I fix my air height depending on the mass flow rate. So everything is fixed. But now I move my probe from near to the bottom towards the interface. So I have a traverse which allows me movement up to zero point 0.1 millimeter of precision. So let us see what do I observe near to the wall. As I said, I have a curvature. So when I go very close to the wall, I am not getting any signal. See, because of the curvature, and I have almost zero velocity near the wall and no velocity signal here. Now I move it up. So from A, which is very close to the wall, I move to B. I get the velocity. This is the magnitude of velocity that I am getting, 0.04, close to point. And this is the perturbation level of velocity, correct? That is what I observe. I go to from point B to point C. This is my perturbation in velocity. The magnitude has increased. As you know, the liquid velocity is going to increase from the wall towards the liquid, towards the interface, because there is a high gas flow at the interface, which will give it's like a Poisson kind of a flow, where this wall is giving the velocity to the upper layer of the liquid. So now I go from point C to point D, that's closer to the interface. You see the perturbations have increased, but this is a flow which is purely stratified. There is no waviness at the interface. So my fluctuations that I observe are purely due to the turbulence that is there in the liquid phase. So I get signal which is at 11 millimeter from the wall. This D is at 11 millimeter. The interface is 13.35 millimeter. How do I estimate? Now I go from 11 millimeter to at the interface near to 13.35, correct? This is near to 30. I still get velocity signals because I have pressures in the liquid. But as I go beyond this, just on the other side, I get no signal. Why? Because there are no pressures there. It's air phase. So I moved my traverse very, very slowly, at a very small jump on of 0.1 millimeter from E to F, so as to know exactly where I stop getting any signal. So where I stop getting any signal is the height of the liquid. So that is how the liquid height is known, utilized very precisely through the LDV. And while Mahesh was doing experiment, we emphasized on, at that time we did not have liquid, this LDV, but we did through visual observation the liquid height and wanted to note the critical liquid height beyond which slug is formed. But today we are able to very precisely tell the critical liquid height beyond which we observe slug. Now this is a result which shows how the liquid height to the diameter ratio, this is the liquid height to the diameter ratio, changes as your superficial Reynolds number of liquid and gas changes. So if you see at very low value of superficial Reynolds number of liquid and high value of superficial Reynolds number of gas, your liquid height is very low, because the liquid mass flow rate is low and gas is trying to suppress the interface. And then as you go on reducing your gas mass flow rate, obviously the liquid height is going to grow from 0.4 to it can go to 0.48. Now, as you go on increasing your superficial liquid Reynolds number or liquid mass flow rate further, you reach to a point, 0.55 points. Beyond this, when it goes beyond 0.5 or closer to 0.6, you will not be able to get stratified flow. It will convert into either a plug or a slug. So we could only measure till liquid heights which are in stratified or very stratified regimes, and how is the variation. Now, how is the local velocity variation in the liquid plug, in the film, liquid film? So if you see, when I have a very small uh, range of gas superficial Reynolds number 750, and I vary my liquid superficial Reynolds number, I am getting a parabolic kind of a flow. Parabolic, not parabolic, going from 0 to maximum velocity at the interface where the gas is driving the interface. So the gas is creating the velocity at the interface. So this is my gas velocity at the interface, and it is parabolic, almost parabolic, at low value of superficial gas flow and low values of liquid Reynolds number, as the Reynolds number varies. But when I increase my superficial gas velocity for these set of Reynolds number, you see my velocity profile tend to be an S curve. So why this S curve? Because at the top, the gas is trying to move the interface at a very, very fast rate, where while because the liquid superficial velocity is same, the liquid is not able to adjust at the mid. So it is actually creating an S curve. And you see the magnitude of the S curve. It goes on increasing as the gas superficial velocity increases. So from a parabolic profile, we tend to get an S-shaped curve for higher values of superficial velocity of the gas in the liquid regime of the stratified flow. Now, we also wanted to get the jump in velocity and correspondingly jump in pressure through our LDP measurement. So what we did is we captured continuously the velocity signals as 4 slugs moved through the pipe. This is 1, 2, 3, and 4 slugs. 4 slugs moving. So if you see the velocity distribution, you have a gradual decrease, and then there is a sudden growth. And then this is the liquid slug, and then again the gradual decrease, sudden rise, and then the slug regime. I'll show you pictorially how this changes. So you look at this picture. I have a liquid slug. This is my film, and this is the bubble. And this is where my probe is. When this bubble is moving and the bubble tail is about to come closer to my interface, that is the location A. This is the kind of velocity signal I get, which is actually the velocity of the film. The film is at a very low velocity. So the very low velocity film velocity I am able to capture before the liquid slug comes closer to my probe. As soon as the liquid slug crosses the probe, see, as soon as it crosses from B, it crosses the probe. See, the area available is increasing. Now you have got the liquid slug velocity. See the jump in velocity from B to C. Jump in velocity because of the larger momentum of the slug. Now this is the location of the plug. This is the location of the probe for condition D, where you have the slug, the entire liquid slug here. This liquid slug is moving. The next bubble is entering here. You see, the probe is here. So what you get here is the complete slug velocity from C to D to E. Now, when you come to F, when is it F? When this bubble has crossed over the probe. When this from E to F, you see, I am reaching to the liquid film. There is a degradation of velocity. So the entire the distribution of velocity in the liquid plug, in the film, and I could capture very clearly with my LDB probe, and that gives sense also. So this surge in velocity is going to talk about local pressure drop there and will lead to slug formation. What about the velocity distribution in the plug or in the liquid slug and the film? See, the velocity distribution is parabolic in the plug or the slug regime. But in the film, it is linear, almost linear, with small amount of S curve because of the bubble moving with high velocity. So in this film, the velocity is almost linear with a small jerk because of the bubble velocity. So it's almost linear in the film. So in this film, the velocity is linear. But in the slug, this portion, the variation is parabolic from one wall to the other wall, from 0 to 0. It's the entire slug is moving through the pipe. Okay, now I come to the last section of my discussion. This is what we have proposed to the industry, how they can safeguard their pipes, how they can, what we propose is a small algorithm, a recurrence algorithm. Now this recurrence algorithm is for analyzing their pressure perturbations. So we developed a recurrence algorithm, and this recurrence algorithm I have given. So recurrence algorithm provides the recurrence plot and the recurrence quantification parameters. So either from the plot, they will be able to know, because industrial pipes are all opaque. That's very important to be told at this stage. All the experiments that we did in the lab are on transparent pipes. See, this pipe is transparent. Whatever experiment I did, all are on transparent pipes. I have shown my experimental test facility. See, these are all transparent pipes. But when you go to industry, they cannot visualize what is going on inside. They cannot know whether it is plug flowing through the pipe or it is liquid slug flowing through the pipe. How do the industry know what to expect inside the pipe? That's what was the point. So they said, we have all opaque pipes. Now, in the opaque pipe, how do we know what is the flow that is happening inside? So for that, we said, fine, you install pressure sensors in your pipe. So we shall also install pressure sensors in our pipeline. We are able to do two things. We are able to visualize, and we are also able to capture the pressure. So through visualization, I know what is the flow happening inside, and the corresponding pressure signals I have. Now these all pressure signals are non-linear. If I can do a non-linear signal analysis and generate a qualified, a quantified data or a qualified, what is it called, pattern, then, and these patterns are significantly different from one regime to the other regime, then you can use these maps to identify what kind of flow is happening through the pipe. So we have used the pressure sensors. So I have told you I have one pressure sensor which is at 3 meters from the inlet, another pressure sensor which is at 8 meters from the inlet. So these two are for measurement of pressure drop. And I have 4 pressure sensors which are very close by. And these pressure sensors give me the pressure signals. So these 4 pressure taps give me pressure signals. So, and I wanted to see the pressure signal corresponding to the intermittent regime as well as separated regime. I have shown you these intermittent regimes. Now, recurrence analysis is the mathematical tool. I am not going into the mathematics. So basically what we do is we develop a phase space trajectory, and from the phase space trajectory, depending on the recurrence parameters, this delay, range, normal, rescaling, radius, and line, we develop the reference plot. So this is a recurrence plot for a cosine signal that I have shown. Now, this is for a stratified flow. This is the kind of signal, pressure signal, that I get for stratified flow. So what I do is I convert this time versus pressure signal into a phase space trajectory. This is what is a phase space trajectory. And in this phase space, I see the recurrence of the data points. And then I convert this phase space trajectory into a recurrence map, recurrence plot. So this is the kind of recurrence plot. So if I zoom, this is the kind of behavior. We can analyze this behavior to show where is the liquid film, where is the liquid slug, where is the bubble. So this is the kind of recurrence plot that I generate through the soft tool that we have created, which takes the signal and converts into a recurrence plot. Similarly, this is the kind of pressure signal we obtained for a wavy flow, and this is the kind of recurrence plot we generated. When we went to plug, this is the kind of signal that you see, pressure signal that we got. This is a zoomed portion of the pressure signal. This is the kind of uh, the recurrence plot that we have generated for plug flow. If you look at this less aerated slug flow, see the pressure, the recurrence plot. See, the recurrence plot is going from a smooth recurrence plot to a grainy recurrence plot for plug flow, to a very checkerboard kind of a recurrence plot for slug flow. See, it's almost a checkerboard kind of a. So when we told, when you get the pressure signal and our soft tool gives you a grainy kind of a signal, then be aware, well, I can expect plug now onwards. So the control panel person who gets the pressure signal, and on his monitor this recurrence plot appears, he should be now careful. Well, now I can expect a slug. If I increase small amount of liquid velocity or gas velocity, I'll have a less aerated slug. And for a highly aerated, see how checkerboarding is, how densely distributed the checkerboarding is. So we have given them a small soft computing tool through which they can get from their pressure tappings the pressure signal and convert it into a recurrence plot. From the recurrence plot, they are able to tell this is the kind of flow which is happening inside the pipe. This is the flow that is happening now. And whenever they see a grainy structure, immediately alarm bell rings. Now be careful. Don't change any parameter. So this is what we have contributed. In fact, we have gone ahead to measure all the recurrence quantified parameters also, entropy, trend, trapping type, and now we are working on showing the variation of these parameters along with from stratified to low aerated slug to high aerated slug. That is sometimes other I will discuss. So finally, our contribution to the industry is, when you get a homogeneous recurrence structure, be very, very happy, nothing to worry about. Get a grainy structure, starts worrying. When you get a checkerboard structure, you are sure that the slug is flowing through the pipe. With this, I come to the end of this discussion. Thank you very much for patient hearing. Any questions are welcome.
Thank you.
I
So,
hope
audience,
I have taken your exact 2 hours of time, as you say.
exactly. It was an enjoyable this thing. Audience, we have one question. Atuf, Miss
Good
Atuf.
evening, sir. Sir, I'm Atuf Sajjad.
Yeah.
Yes, sir. Good evening, sir.
Good
Sir,
evening.
I'm Atuf Sajjad,
Yeah.
undergraduate student at NIT Srinagar Mechanical Department.
Okay.
So I want to ask you, what are gas liquid two-phase flows, and
Okay.
where are they commonly encountered in industrial settings?
Well, I please repeat the second part.
Sir, and where are they commonly encountered in
Okay.
the industrial settings?
Okay. Okay. I have shown that in the beginning.
Yeah.
I'll show here. Here. So you get gas liquid flows in petroleum industry, petrochemical and chemical industry, geothermal industry, nuclear industry. Does that answer your question?
Yes, sir.
Hello? Hello?
Yes, sir.
Ah,
Yes,
And
sir.
gas liquid two-phase flow is simultaneous flow of gas and liquid through the pipe. See, gas and liquid flowing through the pipe. But the interface now deforms because of large change in density, and you get different kinds of flow patterns. Correct? Some of them are hazardous for the pipe.
Okay, sir.
Okay, does
Thank
that answer your question? Anything else you wanted to
you.
know?
Yes, sir. Yes, sir.
Yeah.
No, sir. Thank you.
Anyone else? कोई हाँ you can ask. uh, you can ask number one.
Hello, sir.
Yeah.
My name is Danish, and I'm pursuing MTech Thermal Engineering in NIT Srinagar.
Yeah.
So first of all, I would like to thank you for giving us your precious time. You really made everything smooth and lively, and I guess this is what experience is all about. Thank you so much, sir. My question to you is that we are talking about straight pipes, but if
Yes.
there is any bent in the pipe,
Yeah,
then
that's it. Yeah. We are working on inclinations. We are also going to work on bends now.
okay, okay,
That
okay,
is our target, but we have not done.
okay, sir. We have not done yet.
Yeah, I have not done.
Okay, okay. Thank you, sir.
We are going to work on it. Yeah. We have
And
some other targets also to look into the corrosion erosion phenomena
yes,
on low quality steel pipes in the long run. Yes.
so these parameters won't work on like vertical or inclined.
No, vertical, the regimes will differ. We have experiments done for different inclinations of the pipe, keeping the petroleum pipelines in mind. Inclinations of plus or minus 5 degrees. We
Okay,
have data available for that,
okay.
how the regime map changes.
Sir,
I have
sorry
not
for
shown it here.
yes, sir, yes, sir. Sir, sorry for taking one more minute.
Yeah,
Sir, if velocity of gas and velocity of liquid is not same, right?
yes,
There will be I think there will be the due to velocity difference there will be cause of Magnus effect.
yes, possible.
Is that the reason of waviness?
No, actually, the reason is the perturbation at the interface created by the velocity, not the Magnus effect.
Okay, sir. Does Magnus effect play
And
any
it
role?
is actually a Kelvin-Helmholtz instability.
Sir, does sorry, sir. Does a Magnus effect play any role in it?
No, no, not here.
Okay, thank you, sir.
So Mr. Koshan.
Good evening, everyone. Good evening, sir.
Good
I'm
evening.
a senior undergraduate student at NIT Srinagar. So
Yeah,
I wanted to ask, what role does this CFD, this computational fluid dynamics, play in studying gas liquid two-phase flows and
yeah.
designing
What
the
role does
industrial?
it play?
Yes, sir. Yes, sir.
Yeah. So one of my group of students are working on developing numerical algorithms to capture these complex patterns.
Okay, sir.
Correct. So we
Mhm.
want to capture these patterns on the computer screen, not doing experiments. Correct.
Okay.
Yeah. Now where is the trouble? So if the physics is very well known, then the computational tool will be able to emulate the physics.
Yes, sir.
But the question here for intermittent regime is the physics itself needs to be understood. How the aeration happens, nobody knows. Unless the physics is known, how the numerics will be developed.
Mhm. Got it.
So if you look at computational fluid dynamics, the first part of computational fluid dynamics is mathematical modeling of the flow scenario. How do you
Exactly.
develop a mathematical model if the physics is not very clearly known?
Yes, sir. Yes, sir.
Yeah. That's where is the hindrance in a CFD tool being used in these complex regimes.
Okay. Yes, sir. Yes, sir. Got it. Got it, sir.
Mr. Hazik.
Sir, good evening, sir. I am Hazig from Mechanical Department, undergraduate student.
Yeah.
Sir, I would like to ask, how do the physical properties of gas and liquid phase affect the flow patterns in gas liquid two
True,
phase flows?
true. They have a
Just to
lot
get
of effect, but here when we do experiments, no, we do not allow the temperature to vary so as to vary the flow properties at all. So these are all for constant values of flow properties, fluid properties that we have done, not flow properties, fluid properties. Constant values of gas property, constant values of liquid property.
Sir, how significant of a effect would they
They
have
are
if they would have
significant.
been
So
included?
supposedly we have done some experiments by adding surfactant to the liquid, and that has changed the flow regime map itself because surface tension gets predominant in a surfactant mixed water. So the transition lines that I have shown in my uh, slide, no, in my presentation, say, let us say this transition line, this transition line itself will shift. This line may shift downward or upward depending on how surface tension is going to influence the flow.
Okay, sir.
Yeah,
Thank you, sir.
you are welcome.
Miss Falak, Miss Said Falak, huh?
Good evening, sir.
Good
I
evening.
am Saeed Falak, a mechanical third year BTech student at NIT Srinagar.
Good.
And I wanted to ask, like, how can a flow control device such as baffles and separators be used to promote a more stable flow pattern in gas liquid two-phase flows?
Yes. So, supposedly you want to break a slug, correct? So
Yes, sir.
what you can do is you can inject liquid from the upper wall of the pipe, correct?
Okay,
So
sir.
these flow control devices either inject or suck so as to diminish the slug, so as to destroy the slug, correct?
Yes, sir.
Yeah.
So next we have Tawsif Mushtaq. You can
Good
also.
evening. Good evening, everyone. I'm Tausik Mushtaq, senior undergrad from NIT Srinagar. And my question is that what strategies can be used to control the flow rate of gas liquid two-phase flows and avoid intermittent flow?
Yes. The strategies, industrially, there are slug catchers which are used. They catch the slug, eliminate it from the passage. But the problem is they do not know what is the length of the slug for which the catcher is to be designed. So they hypothetically design a slug catcher which can capture slugs of certain length, and beyond that or lower than that length it cannot capture. So and then they go downstream and increase the slug frequency.
So fine. That's anyone else? I think it's done. So I have some doubts. I need
Yes, yes,
to
Adnan,
help me.
please.
It was a very good presentation. So, Professor Banerjee, you were talking about use of pressure sensors for measurement of pressure signals.
Yes,
Uh, did you find a match between the pressure signals and the flow visualization patterns?
yes, yes.
Did you find that
We-
match? It was just matching
yes,
exactly
yes,
while you were
yes,
having a certain spike, and
yes,
you it was
yes.
corresponding to what you were generating in the flow pattern.
Yeah, in fact, not only the visualization with LDV experiments also.
Hmm. Okay, that's fine. So I saw your Strohal number, which I was just asking you in the beginning. Nah, what was the oscillation of the frequency of that thing? Nah? So you that thing was quite clear to me.
Yeah,
So it is. So anyone else wants to ask? So your setup is a very huge. You have invested a lot of money there. So it's a
yeah,
huge facility.
yes,
So envy this facility.
yeah,
So I'm highly. I'm thanking you on behalf of mechanical department and my organizing committee. So you have
yeah,
spared your precious time and your precious result to our students. Actually, one more. Akib, are you there? One of
yeah,
our participants is asking.
yeah, yeah. So this
Akib
is
is
a very
asking.
interesting question. I think he
Boundary
has
conditions.
chat box. He has put it up. Boundary layer. Yes.
Uh-huh.
Yeah, it's a very important, interesting question. So we
Yeah,
will
yeah.
have boundary layer in
Uh-huh.
the wall attached to the liquid, boundary layer in the wall attached to the gas, and boundary layer near the interface as well.
Yeah, yeah.
Yes,
But
capturing
who can
that is
be
also our target. The interfacial boundary layer. Very, very precise experiments you need to do.
You have to do. Okay, fine. That's fine. So I'm thanking you on behalf of mechanical department and our organizing committee of this workshop. So you have spared your precious time and you have just shown wonderful results. In fact, you have just shown a roadmap to our senior UG students, PG students. So the opportunities in research in real world problems. So
Yeah.
I'm looking forward in inviting you again for such these wonderful talks.
Yeah, it will be my pleasure to come to Srinagar. I have visited Kashmir when I was a small child.
So, so I give my
Yeah,
promise
maybe I
this
was
time,
5 or 6 years
this
old.
time, this time, inshallah, you'll come
I
here.
would love to
I
come to
think
Kashmir
just
sometime.
plan in July you'll be here for
Yeah,
evaluation
yeah,
of
yeah.
our MTech thesis. At least
Yes.
you can come there.
Yeah. And I invite all of you to my lab sometime. Do visit. I
Okay.
shall be happy to show you my setup. Thank you very much.
Charlie, thank you. Okay, bye bye. Good night.
Bye bye. Thanks.